Example 1. Determine whether this ordered pair is a solution to the system. Well, if it's a solution to the system, that means it is on this line if we graphed it and this line if we graphed it. We don't have to graph, though, to decide this. We can just plug in this x and y value. Okay, so looking at the first one here, when I put 5 in for x and 1 in for y, do we get an 8? Well, this becomes 5 plus 3. Yes, we do. It works. That makes us happy. Now, you can't just check it in one. You have to check it in the other. Okay, so does 2 times x, which is 5, minus 9 equal y, which is 1? This is what we're questioning. This is 10 minus 9. Yes, it equals 1. That makes us happy. Therefore, yes, 5, 1 is a solution to the system. Okay. Let's look at example 2 here. For example 2, they want us to solve this system by graphing. Okay, I'm going to use technology to help me. When I try to graph by hand, I always muck it up. So I'm going to grab my calculator and I'm going to put both of these in. But first, I'm going to solve each one of these equations so that y is alone. So the first one, I'm going to subtract 2x on each side. I would get a minus 2x, and then there's a minus 8 already there. Okay, the next one, solving this one for y, I'm going to subtract the x, which would be a negative x minus 1. And then I'm going to divide negative 1 so that y is positive. So if I divide everything by negative 1, I'll have a positive x plus 1. Okay, so I'm going to plug these two into my calculator and see what I get. So first equation when we solved for y was y equals negative 2x minus 8. The next one is x plus 1. I might have to change my window. No, I do not. Looking at the graph here, I can see that they intersect. I can trace along it, or remember from prior videos, I can do second calculate, which is up there along the top row. And I'm going to go to intersection, which is option 5. Enter. It's asking me, is this one of the lines? Yes. Enter. Is this one of the lines, the red one? Yes. Enter. If I want to guess, I can. I usually don't bother. It looks like the point of intersection is negative 3, negative 2. So now that's doing it by graphing, solving by graphing. And now example 3 is solving by substitution. Okay, so let's solve by substitution. So substitution, we are going to take one of the equations and we're going to solve it for one of the variables. So if I add x to both sides, I will have y equals negative 5 plus x. Okay, now I'm going to take the next equation and I'm going to, instead of plugging in a y, I'm going to plug in this equivalent to y. So it will look like 2x minus 5y. That equals 1. And in the y spot is negative 5 plus x. Okay, so clean up, distribute. Simplify, I've got some like terms here. So I have negative 3x's plus 25 equals 1. I'm going to subtract 25 on each side. And I'll get a negative 24 on the right. Divide by negative 3. X is equal to a positive 8. I'm not done though. That's just the x. I need to find the y. So it doesn't matter which equation you use. Okay. You could even come up here and use this one. Okay, and I actually might do that. If y is equal to negative 5 plus x, and I know x, I can plug it in, and I found my y. So that means the solution is 8 for x, 3 for y. Remember, it's always alphabetical. Now, I just used, basically this top equation to find the y value. So I'm going to use the bottom equation to just do a check to make sure that I am correct. So second equation is 2 times x minus 5 times y. And does that equal 1? This is 16. This is 15. Yes, it does. I am happy with my solution. Okay. Let's keep going. The next method's not substitution. The next method is going to be the addition method. Some people call it addition method. Some people call it, oh my goodness, how am I spacing on this? Elimination method. Okay, so elimination and addition are the same thing. So here's what we're going to do. This equation is set up very nicely. I got x's over x's, y's over y's, equal signs over equal signs, and constants over constants. And I am going to simply add these together. Now, the reason some call it elimination is because when you add them together, you eliminate a variable. So my x's actually go away. When I add, I will get 3y's is equal to 2. So for y now, y is equal to 2/3. If I know y, I can come back, I can plug it into any equation and solve for the corresponding x. So I'll just go ahead and use the top one. We call this back substituting. I don't know x, but I do know y. Okay. This ends up being 4/3 equals -1. I'm going to subtract 4/3 on each side. X is equal to a -1 minus 4/3. Well, 1 is a 3/3. Now I have a common denominator. X is -7/3. So if I've done everything correctly, x is -7/3 and y is 2/3. Okay. To check my work, I would probably not use the top one because that's what I used right here to find the x value, but I could check it using the bottom one. So if I wanted to do a little check here, does a -7/3, which would make it a +7/3, plus 2/3 really equal 3? Well, that would be a 9/3, and yes, it does, so I'm happy. All right, we're going to do addition method a couple more times here. This one, we can see that when we add them together, it doesn't eliminate x or y. I'm going to erase this in a second, but this would be 4x's and 3y's equals 0. Well, that's not helpful. Yeah, it's another valid equation, but it doesn't help us solve for just x or just y. So I don't want to do that. Instead, I'm going to multiply one of these equations by a number conveniently, okay? Any equation, I'm going to do the bottom one here, can be multiplied by any non-zero number. So I'm going to take this equation, the bottom one, and I'm going to multiply it by, and I'm going to choose -3, and you'll see why here, okay? If I do that, this equation, everything on both sides, okay, you have the equal sign. This equation will be a -3x plus 6y equals a -33, okay? Top equation I'm not changing. Didn't multiply that by anything. So that's just 3x plus 5y equals a -11. Now that addition method is going to come into play, and we can see that it will eliminate the x's. Add them 11y is equal to a negative 44. Divide 11, y is negative 4. Okay. I'm not done though. I need to now go back and find the corresponding x. Again, it doesn't matter which equation you use. I'm probably going to use this one right here. X minus 2y, and y is a negative 4, equals 11. So x plus 8 equals 11. Subtract 8 on each side. X is equal to 3. So what did I find? What did I find? I found that the solution is 3 for x, negative 4 for y. And there's the solution to my system. Okay? Certainly, I could plug it in to check. I wouldn't use the bottom one because I just used that to find the 3, but I would use the top one, okay? So if I use the top one, 3 times 3 is 9. 5 times a negative 4 will give me a minus 20. Does that equal negative 11? It sure does. I'm content with my solution. Okay, addition method, but currently nothing eliminates when I add. So I'm going to multiply. We've got, obviously options. We have to pick, do we want to eliminate x or do we want to eliminate y? Let's choose, it really doesn't matter. Let's choose to eliminate y. So this top equation, if I'm going to eliminate y, that means I need this and this to be the same number but opposite signs. So I'm going to multiply the top one by a positive 10, okay? And I'm going to multiply this bottom one by a 3, okay? What will this look like? The top one will be, everything gets multiplied now, 20x plus 30y equals, this side too, negative 160, okay? The next one will turn into 15x minus 30y, which is what we were after, right, is equal to, this side too, 90. Now, if I add them together, the y's will go. We have 35x is equal to a negative 70. Divide by 35, x is equal to a negative 2. I like it, but I'm not done. I need to go back and find the corresponding y value. So pick an equation, doesn't matter which. I'll use the top one. 2 times x plus 3y equals negative 16. So negative 4 plus 3y is negative 16. Add 4. Positive 3y is equal to a negative 12. Divide by 3. Y is equal to a negative 4. So my solution here is negative 2, negative 4. Okay. If I was going to check it, I would use the bottom one because I used the top one to find the negative 4. So my check would look like 5 times negative 2 is negative 10 minus 10 times negative 4, which is a positive 40. And does that equal the 30 that it should? Yes, it does. I am happy. Moving on. Here it says addition, and we've added fractions. So for most of us, that introduces a new level of difficulty. Let's clear fractions first. Okay, if you don't like fractions, it's okay. Let's clear fractions first. If I don't want any fractions, this one I'm going to multiply by 6. And the reason I'm going to multiply by 6 is when I distribute the 6, nice things will happen. Like this first fraction will become 6x over 3, which simplifies to 2x. this one will become 6y over 6, which simplifies to just y. And on the other side of the equal sign, we'll have an 18. Okay, let's go to the bottom one. For this one, to clear the fraction, I'm going to multiply by 4. When I distribute it, this one will become 4x over 2. The next one will become 4y over 4. And on the other side of the equal sign, we'll get a 4. The nice thing about this is I now can do the next step of, adding them together. If I needed to multiply by something else, I certainly could, but I conveniently see that these will cancel when I add. So I will have 4x equals 22, which means x is 22/4-ish, which is 11/2, or 5.5 if you want. I'm going to keep it 11/2. So now that I know my x, I'm going to go back and find my y. And I really can use any equation because technically they should all be right? So I am going to pick this one. This is why not? So if I pick this one, I'll have 2x, and I know x is 11/2, plus y is equal to 18. Well, it's 11 plus y equals 18, which means y, subtracting the 11, y is equal to 7. So basically my solution here is 11/2 for x and 7 for y. And I certainly could double check that. Okay? I'm not going to for the sake of time, but I think you understand. You pick, if I was going to do the check, I would do the original 2 equations, plug them in, and make sure it works. Okay? All right. Next, solve the system. They're not telling us what method to use. We can use any method we want. Okay? It's not lined up nicely for the addition method. We would have to rearrange for that. Okay? If you rearrange for that, I would change this one around so it's an x plus a 2y equals 9. And then I would focus my attention on these two. Okay? Now, if I took the bottom one and I multiplied it by a -1, I would get the top stays, right? X plus 2y equals 13. Negative x minus 2y equals -9. When I add, those are gone and those are gone. That's a 0 on the left, and on the right we have a 4. Now this is alarming. There's no x's, there's no y's, so I can't solve for them anymore. And I have something that is a false statement. So when we get false statements, like I can't make that true, there's no x's in it, there's no y's in it. When it is a false statement, that means there are no solutions. Okay? Now, graphically, here's what this means. Graphically, let's see. Graphically, we have 2 lines and they don't intersect. So if you graphed them, there is no point that these 2 lines have in common. All right? Okay, so if it's a false statement with no variables, no solution. All right, let's go to the next one. This time, let's see. I am going to try to eliminate by adding the 2 together. So I think what I'm going to do is I'm going to take this top one and I'm going to multiply it by a -3. Okay, which will give me a -3x minus 9y equals -6. The next equation I didn't touch. 3x plus 9y equals 6. And when we add these together, we get 0 equals 0. Now, it wouldn't have to be 0 equals 0. It could be any true statements. It could be 5 equals 5. It could be 10 equals 10. -3 equals -3. If you get something like this that is true, right? Different than here, right? Up here, it was false. Here, it's true. When you get a true statement, no x's, no y's, but it's a true statement, it means that there are infinite solutions, okay? It also means that if we graphed them, here's one of them, and here's the other one. It is the same line, okay? So when it's the same line, we can say that the solution is, there's two different ways we can write this, okay? The solution is, there's infinitely many, but what are they? They're all the x, y pairs such that, and it doesn't matter which equation you use, okay? I'm going to use this top one, such that x is equal to 2 minus 3y, okay? What do I mean by that? It means that it's not just any old x with any old y. There's a specific relationship. All of these infinite solutions have a specific relationship with each other, and it is that, okay? And then y is any real number. I'm going to abbreviate real number with the symbol, okay? That means if y was 0, you'd have a specific x, and you could find it. It would be 2. If y was -1, you'd plug it in here. You'd get a specific x that goes with it. So there's infinitely many solutions, but they have a relationship with each other, the x's and the y's, okay? Whew. The most ideal situation is when we have a two variable, x and y typically, although it doesn't matter, system, and there is one solution, okay? As you can see here, we have an orange line and a blue line. They intersect at one particular spot. If this was the variables x and y, we'd have our x value, our y value, and have one solution. Now, there are other situations where we can be trying to solve the system of equations and end up with no solution. That would be this next situation here. If we graph these two equations and they don't intersect anywhere, meaning they're parallel if it's a two-dimensional plane, then there is no solution. There's no xy pair that would work for both equations, and there's no solution. When this happens, we call it an inconsistent system, okay? Because there is no solution. Now, when we have this third scenario here, which is this last one, the reason that you can't see the orange line that's been graphed is because the system of equations has produced the same line twice. So that means there's infinitely many points because it is the same line. And when that happens, it is a dependent system. Okay, there are infinitely many solutions. And we'll talk about how we write that as we get an example, okay? So let's keep moving here. All right, I got two more also. Let's see if we can push through here. This one says, given the cost function and the revenue function, find the break-even point and the profit function. Okay, so if you were to graph this, okay, the cost function, here's my 35,000, and it's got a positive slope, so it's going to be something like this. This is the cost function, okay? The revenue function has a steeper slope, okay? The break-even point is when cost and revenue are equal to each other. So break-even is when cost equals revenue. Okay. Profit is when revenue is more than cost because you're bringing in more than you're spending. So right now it says find the break-even point. So the break-even point is when they're equal. So I'm going to substitute into each one of these spots. Okay, R of X is 1.55X, and C of X is 0.85X plus 35,000. All right, I'm going to subtract the 0.85X over. We'll have 0.7X is equal to 35,000. Okay, divide by 0.7, X is equal to 50,000. So I don't know what this was of, but the X is the items, right? I'm going to say items. Okay. And the Y value there is the corresponding Y value. You just plug in that X into either one of these because we know that they're the same. Okay. So break-even point is 50,000 items. And what would the Y value be? Plug in 50,000 into there and calculate it. $77,500. And that is my break-even point. Now, when they say profit, profit is, what is this gap difference? So revenue minus cost. So profit function is the revenue function minus the cost. So how much you're bringing in minus how much is going out. So my profit function will look like 1.55x minus 0.85x plus, not plus, it's going to end up being a minus, right? Let's change this so it makes more sense. Minus 35,000 with the minus sign in front of all of this. Now, could I distribute the minus sign and clean it up? I sure can. Okay. And if I do that, I'm running out of room here. My profit is going to be 0.7x minus 35,000. There's my profit equation. Okay. All right, let's do this one more time. All right. Tickets to the circus. The cost of a ticket to the circus is $25 for each child and $50 for each adult. On a certain day, attendance at the circus is 2,000 people, and the total gate revenue was $70,000. How many children and how many adults bought tickets? Okay, so there's two equations going on here. One is going to be about the money, and one is going to be about the number of people. So the easiest one is so many children and so many adults equaled 2,000 people that attended. Okay, that's about the number of people. Next, it's about the money. Each child was $25. So $25 times the number of children plus $50 times the number of adults. That's how much money for each, right? And the total is $70,000. It's a system of equations which we are going to solve, okay? Let's see. Let's multiply. I'm going to do the addition method. So let's multiply this by negative 25. So what will that look like? Negative 25c minus 25a equals negative 50,000. Okay. Second equation, I didn't change at all. 25c, 50a, 70,000. Addition, positive 25a equals 20,000. Divide by 25, a is equal to 800. So there are 800 adults, okay? Well, how many children? Well, I'm going to come back up here. I'm going to take this equation. There were 2,000 tickets sold. So children plus 800 is equal to 2,000 tickets. Subtract 800. We get 1,200. What does this mean? This means tickets sold for children, 1,200. Tickets sold for adults, 800. There you go. Systems of equations with two variables. Remember, we get one solution, we can get no solution, and we can get infinite solutions.